Hi everyone, today I want to talk about an approach combining reinforcement learning with imitation learning to deal with near-accident scenarios in driving. We all have seen autonomous vehicles driving around us, but current autonomous vehicles still cannot handle near-accident scenarios well. Let me give you an example where autonomous cars having difficulty. I've been talking to people who work in autonomous driving, and a common problem they deal with is this plastic bag problem. Imagine that when you are driving your car on the road, suddenly you see a plastic bag in front of your car. What should an autonomous car do in such settings? It would either abruptly brake to avoid hitting the obstacle, but such brakes for every single plastic bag makes the passengers really nauseous. Or the autonomous car can ignore the plastic bag and drive over the bag, but as we have seen, such actions can also lead to serious accidents. Therefore, in near-accident scenarios, we need to balance a trade-off between safety and efficiency. The way we formalize near-accident scenarios is using the notion of phase transitions. Let me introduce phase transitions. A phase transition is defined as large changes in actions required for safe driving under small changes of states. In this example, we have a red Eagle car trying to cross the intersection, but there's a large gray wall occluding the red car's field of view. When the Eagle car drives close to the intersection, a blue car suddenly appears from the occluded viewpoint, causing a near-accident scenario. The red car now must slow down to avoid the accident. This is an example of a phase transition because a small change in the blue car's state, such as acceleration, dramatically influences the red car's action of stepping on the gas or the brakes. These phase transitions naturally create different modes of driving. For example, depending on small changes in the blue car's driving, the red car might aggressively drive forward, timidly stop, or swerve around. Given these modes, the autonomous car needs to decide how to switch between the modes to handle the phase transitions in near-accident scenarios. Here's how we solve the problem. We first learn how to drive in different driving modes using imitation learning. We train a neural network to take a sequence of images in each mode and outputs the action that needs to be taken. Then we need a high-level agent to decide which mode to execute at each time step. We then use reinforcement learning to learn how to optimally switch between modes. You might ask, why don't we simply use reinforcement learning? This is because the problem becomes intractable due to the large state action space. On the other hand, why don't we simply use imitation learning? That is because it would require an extremely large number of expert demonstrations of transitions between different modes. But our approach learns a particular mode of driving through imitation learning and should require fewer expert demonstrations. Also, the high-level reinforcement learning problem is simplified since the actions are discretized. So we leverage the best of both reinforcement learning and imitation learning in our method. In summary, we have designed a hierarchical approach with a high-level reinforcement learning agent that optimally switches between low-level imitation learning policies. We evaluate our algorithm on 5 near-accident driving scenarios. Here I only introduce the merge scenario in detail. In the merge scenario, the red Eagle car is trying to merge into the right lane as quickly as possible. Depending on the space that the blue car gives the red car, you can imagine a timid driver will simply merge behind the blue car, while an aggressive driver will always try to merge between the blue and the green car. We ask users to rate different driving styles, including timid, aggressive, imitation learning, and our approach. Timid driver is learned on demonstrations where the car always merges behind. Aggressive driver is learned on demonstrations where the car always merges between. Imitation learning driver is learned on the mix of both demonstrations. You can see our approach realizes a best trade-off between safety and efficiency, and it is preferred compared to the baseline on a 7-point scale Likert rating. So to summarize, our work proposes a new way of driving in near-accident scenarios with phase transitions by combining reinforcement learning and imitation learning, which optimally balances between safety and efficiency. Thank you.